In the next lesson, we're going to look at a method that's going to help us find the absolute maximum and minimum values for a function under certain circumstances. But before we get to that, I want to look at a theorem and I want to talk about a definition. So we've got a theorem and a definition. Let's look at the theorem. This is called Fermat's theorem. The T is silent, Fermat's theorem. And it says, if f has a local maximum or minimum at a value c, and if the derivative exists at c, then the derivative must be equal to 0. Let's take a look at the graph of the function that we saw in the last video. All right, here we are. Now the theorem says if there's a local maximum or minimum at a number, and if the derivative exists, then the derivative has to be equal to 0. Well, let's see what that means on this graph. Remember, we had a couple of local maximum and minimum values, right? We had a local maximum here. Let's actually draw dots wherever we had a local maximum or minimum. So we had one there, and then we had one kind of at this sharp corner. We had a local minimum there, and then we had another local maximum, and then another local minimum. We're going to ignore the endpoints here. We're just going to look at the local maximum and minimum values on the inside. And this theorem says if it has a local maximum or minimum somewhere, and if the derivative exists, then the derivative has to equal 0. Well, remember, when the derivative of a function equals 0, that means the tangent line is horizontal. And if we look at the tangent lines at these local maximum and minimum values, here we've got a horizontal tangent. And then at the next one, it is not differentiable because we have a sharp corner. At the next one, we also have a horizontal tangent line. Not drawing these perfectly, but you get the gist. And then also at the last one, we should have a horizontal tangent line. Again, not perfect, but you understand. And so if we look at these maximum and minimum values at the points where they occur, all of them have horizontal tangent lines or are not differentiable. The reason that this is true is kind of if we think about a counterexample, if we had a derivative that wasn't equal to 0, if we had a derivative that was equal to 1 or -3 or something like that, well, if the derivative was positive, that would mean that the tangent line has a positive slope, and so we'd have an increasing tangent line. And so it can't be a maximum value because that means it is growing at that point. The same thing is true if the derivative was negative. If we've got a negative derivative, that means a negative sloping tangent line. That means our function is decreasing. And so again, that's not going to be a local maximum or a local minimum. So if we have a local max or min and the derivative exists, then that derivative is equal to 0. And we can think about what this means. It means that if we're looking for local maximum and minimum values, they're going to occur when the derivative is 0 or when the derivative is undefined. And we have a name for those possible values where those might occur. We call them critical numbers. A number c is called a critical number of a function f if f prime of c equals 0 or if f prime of c does not exist. And so critical numbers are the x values of a function where the derivative is 0, which means we've got horizontal tangent lines, or where the derivative doesn't exist. And these are the candidates for local maximum or minimum values. So we're going to be using this later to figure out where we might have maximum and minimum values on functions.